Hey physics! So as I said earlier, there is one more thing that we need to add to our evaluation of circuits and the calculations we do on them, and it's actually not that big of a deal. After you've done current and voltage, this is like small potatoes. It's something called power, and it's so basic I don't even need the calculator on screen for this today. So let me go ahead and introduce to you power. Power is a quantity in time. It's defined as energy over time, and the units of power is watts. Okay, so the unit of energy, of course, is joules, and the unit we would use for time is seconds, which means for all intents and purposes, 1 joule is 1 watt. I'm sorry, 1 watt is 1 joule per second. So 1 watt equals 1 joule per second. All right, so that's cool. What that means as far as like your microwave oven, say, if it is a 1,000 watt microwave oven, it means that when it's on high, it's delivering 1 kilojoule or 1,000 joules per second. That would be at like, perfect efficiency and all that. Anyway, how does this work with electricity? Well, if we're talking about a battery as a source of energy, there's an energy difference between the two terminals. Then as that energy is actually being spread out, it happens over time. Voltage may be static, but current is not. Current always involves a flowing of energy. So if we were to describe power with an equation, it is actually this one. I'm going to write it in another color just so it stands out. Here's our equation for power. P equals IV, where you multiply the current by the voltage. Okay, so there's actually another variation to that which we can take advantage of just in case it's more relevant, and it comes from this. You know that V equals IR. Well, you can take V, substitute that in there, which means that P is also equal to I squared R. Alright, to demonstrate how power is calculated, I'm going to work through one of the circuits that I gave you this week, find the solution to it, and then also show you how to do the power. So, the circuit that we're going to be doing is this one. Okay, so we have here a 9-volt battery. Yeah, we're in frame. 9-volt battery, and the resistors, which I shall number, R1, R3, R2. I'm going to go ahead and just label them like this. R1 is 5 kiloohms, R2 is 10 kiloohms, and R3 is 5 kiloohms. Okay. So this is one of the circuits that you had for homework this week. So let's begin by solving it. First of all, these two resistors are in parallel, okay? Which means that this can be redrawn like this. Where this is R1, and then this is the combination of those two, which we would get like this. 1 over R2 plus 1 over R3. So let's go ahead and work that out. Oops, not a minus sign. 1 over 10,000 plus 1 over 5,000, and it's 3,333.3 repeating. That's a lot. 3,333.3 repeating. Okay, and then these two resistors. Oh, oops. I just noticed my microphone is out of frame. So if I sound a little weird, that's why. I forgot to put the right microphone in place. So these two are... Right, they're going to add up in series, so that's just going to be 5,000 plus 3,333. So if I add to this 5,000, there you go, 8,333.3 repeating. Okay, so the total resistance of this circuit is 8,333.3 repeating. Okay, that's the total resistance, so we should be able to find the total current now from Ohm's law. If V equals IR, and we have a 9-volt battery, that means 9 volts equals unknown current times 8,333.3 repeating ohms. Whew! Let's do that math. 9 divided by 8,333.3. Okay, so it's 0.00108. That's the current. So I can go ahead and conclude that the current through this circuit is 0.00108 amps, aka 1.08 milliamps. Okay, so how about the voltage across, current through, and power consumed by each of the resistors? All right, let's go ahead and do that. So for resistor 1, we know that the resistance is 5,000, and we know that the current is 0.00108. So the voltage across resistor 1 will be 0.00108 times 5,000. That's V equals IR. And so the voltage across resistor 1, oops, 0.00108 times 5,000, it's 5.4. The voltage across resistor 1 is 5.4. Okay, so I've got a current and a voltage. Let me actually write that current. We know the current. It's 0.00108 amps. So what about the power? Well, the power through resistor 1, I should say that power consumed by resistor 1, is going to be I times V. So it's going to be 0.00108 times 5.4. So 0.00108 times 5.4. It's 0.005832. 0.005832. That is how many watts that is. So let me write that in orange just to keep it consistent. 0.005832. That would be in watts, which means we could call that 5.8 milliwatts. Is that a lot of power? Is that a lot of power? Well, in order to answer that question, it would be helpful if you had some sort of electrical device to compare it to. So let me just put this down a quick second and get one for comparison. Ooh. All right. We have here a power adapter for a router And as you can see, its input is 15 watts. I don't know if you're able to see that. It's 15 watts. We just had a 3,000th of that. So this is actually quite little, and this is just to power a router. By the way, it's also worth noting, this is 9 volts, just like that is, and this is 1,000 milliamps, whereas this one is only about 1 milliamp. So this is a very low power circuit.